Alright, this is the fifth and final video on polynomials, and we're going to start off with solving and graphing polynomial inequalities. Okay, we got a couple of those, and then we'll finish up with sketching a system of polynomials that has three solutions. Alright, sort of creative activity there with many different correct answers. Alright, but let's start with number 12. Okay, as I look at this problem, let me tell you what I see. Alright, I'm picturing my x-axis, and I see that I've got a degree 4 polynomial. Now, in general, degree 4 makes some type of a W shape. So I'm seeing that we have less than or equal to 0. So we're asking ourselves, where is the function less than or equal to 0? So if this was the situation, then less than or equal to 0, I'm talking about equal to or below 0. You know what, let me do it this way. So, no. Okay, so this would be where this particular function is equal to 0, and then it would be below 0, underneath the x-axis. So in this case, it would look like this. However, it doesn't always work that way when you have a fourth degree polynomial, a quartic, because sometimes it does something more like this, where it might still make its W shape or whatever, but maybe it only has two x-intercepts. Okay, and in that case, again, if I wanted to know where is the function less than or equal to 0, I'm still talking about equal to or below the x-axis. So here's where it's equal to, and here's where it's below. Okay, but this solution set looks a lot different than what I had before, where I had two different little parts to it. So it would be helpful to know which situation we're dealing with right from the beginning. So if you have access to a graphing calculator, it might be helpful to take a peek at the graph, so you can see, how many times is this thing actually crossing the x-axis. So let's go ahead and do that. I've got a graphing calculator right here. You can just look over my shoulder. Alright, so let's go in and type it in. So it was x to the fourth power and minus 16. Let's see what that graph looks like. Okay, so it seems to only be hitting the x-axis at these two places. Just out of curiosity, I'm going to look a little bit lower just to see what's going on down there. To do that, we could adjust the window, and to lower the floor of this window, we want to lower the minimum y value, which is right now it's set to -10. But if I change this to like -20, for example, then that's going to allow me to see lower. Okay, so now I can see it's almost looking like a parabola. It's not a parabola because it's degree 4, but the behavior is very similar to a parabola. It's only going to have two x-intercepts. So we want the part of the graph that is less than or equal to 0. So it is going to just be one loop going from here to here, and it looks like this is -2 and +2. Alright, let's think about that algebraically for a moment. I could factor this down. Alright, this is the difference of two squares. So, if I set x to the fourth power minus 16 equal to 0, so I could find the zeros, I could factor this. This would factor as x squared plus 4 and x squared minus 4, because this is the difference of two squares. Now, one of these can factor more and one of them can't. Alright, so you can probably realize that x squared minus 4 can factor further as x plus 2 times x minus 2. On the other hand, the sum of two squares is unfactorable, so x squared plus 4 just stays the way it is, can't factor that. If I were to set x squared plus 4 equal to 0, okay, because that's how you find the zeros. You set all of these equal to 0, actually. Alright, these pink ones give us obvious solutions, right? You know, so to get x by itself, here I would subtract 4 from both sides, subtract 2 from both sides, add 2 to both sides. Alright, this is going to give me x equals -2. So right there, that's one of my zeros. That's an x-intercept. It would be -2, 0. And this is going to give me x equals +2. Okay? So look, that's the -2 and +2 that we saw in the graph. Alright, that's where those come from. And the reason why we don't get any additional x-intercepts out of this part is because then we have x squared equals -4. Okay, well, when you square something, it makes a positive number. So there's no solution to this. There's nothing I can square. You know, if I do -2 squared, that's still +4. Or another way to look at it is, if I continue to solve this, I would take the square root of both sides. And I'd do plus or minus. But what happens when you take the square root of a negative number? You get imaginary numbers. So this would be plus or minus 2i. So these imaginary solutions are not x-intercepts. Okay, they don't show up on the graph. So that's why we will only have these two x-intercepts. So as we look at our graph, you know, here's a sort of sketch of sort of what we were seeing on the graphing calculator. And here we had our two zeros of -2. You know, let me just redraw it real quick. Okay, so we just have the two x-intercepts, the two zeros. So we have, you know, I always include 0 in my graphs. So we had -2 and we had +2. Those are the x-intercepts, the only two we've got. And we saw what the graph was doing as we looked at the calculator. There's an x-intercept here, and there's an x-intercept here. And we saw that the graph was behaving very much like a parabola. Okay, and it's not a parabola, but it looked a lot like a parabola. So because we want to know where the function is less than or equal to 0, we look at that and we are looking below 0, below the x-axis, or equal to 0. So let's start with the equal to 0 part. The function is equal to 0 at the x-axis. So these 2 points will be included in the solution set. But we also want the part of the function that is below 0, less than 0. So that would be this part of the function right here. Okay, so if I were to graph these solutions just on a number line, here's what that would look like. Okay, so there's my -2 and my 0 and my +2. Now on a number line, I'm just showing the x values of these pink solutions here. So the solutions begin at -2, they end at +2, and everywhere in between we have solutions. So this would be a graph of the solution set right here. Okay, now if we wrote this in interval notation, okay, which is what they asked for, in interval notation this would simply be -2 to +2, and we will use the square brackets to indicate that the endpoints are included. Okay, so this is the solution to problem number, what problem were we just doing? Problem number 12. Actually, before we move on, I need to point out that we also could have done this problem using the test value method. I went ahead and did it graphically, okay, as you can see, because that made sense to me. But it would have been very easy to do it by the test value method as well. So let me show you that way, and you can do whichever way you want to do it. So we had these zeros at -2 and +2 as we discovered. And this is less than or equal to 0, so we will draw these as closed circles, because that's the equal to 0 part, and we will include those in the solution. But with those zeros, we now realize that we have just divided the number line into 3 zones. Okay, we have our yellow zone over here to the left. Okay, we have a blue zone here in the middle, and then we have a say green zone to the right. Okay, so we have these 3 zones. So if we're going to do the test value method, then what we do is we pick a test value from each one of those 3 zones, and we see if it's a solution to the inequality or not. So let's pick our 3 test values right now. So representing the yellow zone, what would be a good test value to use? Yeah, how about -3? That's the first integer you come to. What about the blue zone? Yeah, 0, I agree. What about the green zone? Yeah, how about 3? That's the first integer you come to. So let's do these 3 test values. And whatever we get, in each case, we're going to be asking ourselves, is that value less than or equal to 0? Okay, because that would make it a solution. So we want to know, is it less than or equal to 0, what we get? Okay, so the value of the function at -3. Okay, now this function is really simple, which makes it pretty easy to evaluate. So I could literally plug these values in. Let me write it over here. So we have x to the 4th power minus 16. So it would be very easy to put these values in here and do, if I do -3 to the 4th power, that turns out to be 81 minus 16. So that is 65. So we can just immediately go, okay, 65, is that less than or equal to 0? No, it's not. And that tells us that the yellow values are not solutions to the inequality. Okay, so let me back that up. So now we could do 0. Alright, if I substitute 0 into the function, well, 0 to the 4th power is just 0, so that gives me -16. Is -16 less than or equal to 0? Yes, yes it is. So that tells me that these blue values here are solutions. And I will show that by drawing a segment here representing all the solutions between -2 and +2. And then how about the green? Well, this is just like what we did before. If I put 3 in here, 3 to the 4th power is 81. Again, 81 minus 16 is 65. So again, I get 65 is less than or equal to 0. Well, no, it's not. So again, that means that these green values are not solutions to the problem. Okay, so that leaves us with this, and then we could easily go ahead and translate that into interval notation, just like we did before. So -2 to +2. So that's how you could do the problem using test values. One more thing to mention as far as evaluating these test values. This particular function was really easy because it was so small, we could just plug in very easily. But for a more complicated function, you might consider using your calculator. Okay, and what I mean is using the table feature. So for example, we had x to the 4th power and it was minus 16. So it's really easy to use your calculator to evaluate these things if you use the table feature. And okay, let's just look at the table real quick. So the table is evaluating each of these x values. Okay, so if I want to know what the value is at -3, I can just scroll to -3 and take a look, and I see, oh, it's 65. So that's the same thing we got when we plugged it in, but look how quick that was. Alright, if I want to know what's happening at 0, I just scroll down. Okay, at 0, that's -16. Same thing we got. And if I want to know what's the value at 3, I just scroll down again. It's 65. Okay, so I can get these values very quickly using the table feature of my calculator, which makes the test value method an efficient way to go very often. Alright, so I just wanted to show you both methods. Okay, now let's do another one, number 13, another inequality. I recommend, now we could solve this as it is, by treating the left side of the function and the right side of the function as two different functions. I prefer to get 0 on one side and deal with that. So that's what I'm going to do. So I'm going to subtract x from both sides. Okay, and I'm going to subtract 4 from both sides. Okay, so if I do that, then what I have now is x to the 5th power. Alright, so bring that down. These are not like terms. I'm not going to put these together. I'm just going to bring down my 4x squared unchanged. And then I'm just going to bring down my negative x. Okay, just brought that down. Now these two are like terms. What happened to my highlighter? These two are like terms, so I'm going to put these together. And together, those make -5. And then this will be greater than 0. Alright, when I see this greater than, I'm thinking above 0. Okay, it'll be above the x-axis. Alright, so next we need to find the zeros of this graph. Now, if we're allowed to use a graphing calculator, why not take a peek at the function and just get a feel for how many x-intercepts we should actually have. We know there will be 5 zeros, okay, but some of those might be imaginary. So those will not really affect, the inequality. So let's look for the x-intercepts on a graphing calculator. Alright, so here's the function typed into my calculator, and please understand it's this new one, the one with the 0 that we're working with. Okay, so let's take a look at the graph and see what we've got. Hold on, I forgot to set it to a normal window. Okay, so here's what it looks like. Now look, looking at this graph, there seems to be only one x-intercept. Only one. Several students of mine who were taking this test, they were desperately trying to find this x-intercept over here. And it doesn't touch. See the space in between? It doesn't reach. There is no x-intercept over here. So don't try to find it. So we just have the one x-intercept. So we could find it on a table of values. Okay, so I'm going to look at the table real quick and take it back. We will not find it on a table of values. It must be some sort of a decimal. So it would be right here between the -1 and the 41. Okay, so just making sure. Yeah, so it's not showing up on a table of values. So we really are going to have to use the graphing calculator to find this. Now, if we're going to do this, here's what I recommend. For me, the easiest way is to also type in the right-hand side of the function, which is 0. Okay, so I'm going to go back. So I have the left side of my inequality typed in, but I'm also going to type in the right side, which is 0. Okay, so it doesn't look any different, but now we have this horizontal line graphed here. So we want to know the intersection between the cubic, well, it's really not cubic, sorry, this is a 5th power. It looks cubic, but it's really 5th power. and this horizontal line. So if we do second trace intersection, so I'm going to choose option 5, it starts running the intersection program. I like to be on the x-axis, so I'm going to hit my up arrow and jump to the x-axis. And I like to go over close to the intersection point, as close as I can get. And then I'll just hit enter 3 times. Enter, enter, enter. Okay, so it gives me the intersection, which is 1.07. Okay, 1.08. I'm going to round it up a little bit. So 1.08 is the 0 of the function, approximately. Okay, so fine. So we found a 0 at 1.08. I'm just jotting that down before I forget. So we've just got that 1, 0. So let's go ahead and draw our situation. Okay, and see what we've got going on here. Okay, so there's a 0, which I always include, and here's 1.08 right here. Okay, I'm going to do this one by test values first, and but then I can also do it graphically. If I do this by test values, then this is what I'm thinking. I'm thinking we have a 0 here at 1.08. So that's going to be an endpoint. I'm going to put an open circle because it's greater than, and so I don't want to include this border point. So I'm going to now look at the fact that I've divided the number line into 2 zones. I have a zone to the left, which I'll call the yellow zone, and I have a zone to the right, which I will call the blue zone. So I need to pick a test value from each zone. Okay, so I'm going to make a little chart here, keep my work organized a little bit. Alright, so in the yellow zone, a good test value would be 0. So f at 0. In the blue zone, a good value would be 2. Alright, now I didn't have to pick 0. Technically 1, the number 1 is in the yellow zone. Or I could have used -1 or whatever. But I'm going to use 0 and 2 because they just feel comfortable to me. Okay, now I could take 0 and plug it into this function for all these x's. But really I can do that mentally, because if this is 0, that means that term will be gone. And if this is 0, then that term is gone. If that's 0, then that's gone. So I'm really just going to immediately have -5 will be the result. And then the question will be, is this greater than 0? No, a negative number is never greater than 0, so that's a no. So that tells me that I will not have solutions over here. I'm going to leave that blank. Another way I could have evaluated this at 0 is I could look at the table. Alright, so if I hit second graph on this calculator, now I'm looking at the table. And so look, the value of the function at 0 is -5. I could do it that way. And that's how I'm going to do it for the other one. The value of the function at 2. Alright, look back at that table. At 2, the value is 41. Okay, so I'm going to jot that down. I got 41. And again, the question is that greater than 0? And of course the answer there is yes. That means 2 is a solution, which means all of these blue values are solutions. So I will show that by drawing an arrow representing all the solutions to the right of 1.08. Okay, so this would be a nice graph of my solution set, and in interval notation that would be round parentheses 1.08 to positive infinity. Alright, so that would be a complete answer to this question. And that's by using the test value method. Now, real quickly, I could have done that using the graphical method. Alright, so I'll just slide over here and show the graphical method. We saw on the calculator that we just have the 1, 0 at 1.08. So there it is. So by the graphical method, we need to sketch this graph. Now, if we didn't have a graphing calculator, it would be very difficult to do. But we did have access to a graphing calculator. So if you look at the graph, you can see that it's doing its wave, but it's not quite reaching the x-axis, and then it's coming up through the 0 right there. So we can just sketch that as well right now. Okay, so we can do this wave thing. Okay, it's doing the wave, and then it's coming up through here like that. Okay, and of course it's going off to infinity and beyond. Now, we want to know where the function is greater than 0. In other words, where is it above the x-axis? Not equal to, only above. So if I want to highlight that, I would do it like this. Alright, I'm not going to highlight the blue dot because I only want the part of the graph that's above that. So that would be like this. Okay, now if I wanted to look at that, just the x values, in other words, if I wanted to flatten this out into a number line graph like the way we express our solutions, I would see that these pink solutions here, they start at 1.08 but not including 1.08. So I'll put an open circle, and then they go to the right from there. So I would draw my arrow going to the right from there. And of course, once again, that would be 1.08 to positive infinity. Okay, so that's how I could have done it using the graphical method, with the help of the graphing calculator showing me exactly what it looks like. So if you're allowed to use a graphing calculator, do it, use it. Without the graphing calculator, you only would have been able to find your 1, 0. In fact, scratch that. You really needed the graphing calculator. So that is it for problem number 13. Okay, now let's look at the 14th and final problem. We're supposed to sketch a system of polynomials that have 3 solutions. Okay, we're just doing sketches. We're not doing any equations or anything. So let me just give you the background knowledge. Alright, a system of polynomials is simply 2 or more polynomials on the same plane, together. So, for example, I could have one polynomial that was a parabola. Okay. And I could have another polynomial that's another parabola. So there, I've just graphed two polynomials. That's a system of polynomials. Now, how many solutions do they have? Yeah, they have 2 solutions, here and here. Okay? So that's one system. Alright, let's look at another system. Okay, let's see. I could have a cubic function. Okay, looking like that. And let's do another parabola, alright, a quadratic. Okay, so this is also a system of polynomials. It's 2 polynomials drawn together. How many solutions does this system have? Alright, this system has 2 solutions. Okay? So you're starting to get the idea, so when I say a system of polynomials, sketch a system, I'm just talking about this kind of a picture. Okay? Here's another system. Because I could do a system, for example, let's see. Here's a cubic again. Alright, here's a cubic. And so this time I'll do the system of a cubic and a line. Okay? So let's say I had a line going like this. This would be a system of polynomials, alright? a line counts as a polynomial. All right, it's a very simple, it's a linear polynomial, but it's still a polynomial. Okay, so this would be a system. How many solutions does this have? All right, this system only has one solution. Okay, so you get it. So our job on problem number 14 was to sketch a system of polynomials that has 3 solutions. So there are a lot of ways to do that. Okay, but so one easy way would be to do a cubic and a line. Alright, if you do a cubic and a line, then you know, if you draw it correctly, then it will have 3 solutions. So that would be like one answer to this right there. Okay, let's see. What else? What if we have a cubic and another cubic? All right, so will that get the job done? So let's see. Here's a cubic, and here's another cubic. Okay, I'm going to make this cubic go kind of the other way. Alright, so there's a system of polynomials. How many solutions does this have? There's 1, 2, 3. Okay, the solutions are the intersection points. So that would be another way of doing it. Okay, I'll just do one more just for fun. Is there a way to do it without using a cubic? How about I'm going to try to do one with a quartic. Okay, so quartic has this type of a thing going on, perhaps. Okay, is there a way that I can do it? Yes, there is. Okay, I'm going to use an actual line from the software here to help me do this properly. Okay, because the way to do it would be to make it be tangent right here at this part right here. Okay, so if I do it like this, then you can see that I will have 3 solutions. I'll have one here, and one here. Okay, so there are many ways, and I'm sure there are more that I just haven't thought about yet. But these are all examples of systems of polynomials that have 3 solutions. So that's how you do number 14. Alright, we have finally reached the end of this journey. If you're doing recovery, you know, if you're my actual student and not somebody on YouTube from Nairobi or India, then you're probably trying to retake this test because you didn't do so well. Please make sure that you can do every single problem on this test. Well, I mean, at a minimum, do every single problem on this test by yourself, not following along with me, but if you sit down with a blank sheet of paper and every problem that comes up, you should just pause the video and do the problem yourself, and then run the video to see if you did it right or not. Alright, if you can do that consistently, then that goes a long way to showing that you're ready for the test. Alright guys, that's it for me tonight. I hope it was helpful. I'll see you on the next video on a completely different unit than this.